So, what is a communication setup? Right? We all know that communication means we should be able to transmit the information from source to destination or a transmitter to a receiver, right? And the information which we transmit is transmitted through a carrier through a channel, right? So the three main building blocks of the communication system or communication, any communication setup is transmitter, channel as well as the receiver, right? So can you give me the most natural example of a communication setup? Yes. So a person A communicates with person B through voice, or AI transmits its signal through the acoustic signals, right, to B. So this is a communication setup. The transmitter is person A, which is using his this system to through mouth. For example, A sees cat, right? And now A wants to transmit this information to B. And B, for B, the receiver part first is ear, right? So what A can do? A will first, A will so these are the lungs which will produce the air, and through acoustic waves we will transmit that information to B. So meaning that transmitter will send the information through carrier to the receiver, and the receiver will extract the information. The receiver will extract the information from the carrier waves. Correct? Yes or no? So, how would you decide the carrier? Okay, let's take one more example first. One more very natural communication system is that our receiver B observes something through eyes, right? And if you want to communicate a phenomenon, for example, zero means when you put this fire, you want to communicate something, right? Or you put a torch, you put a light, and light means there is some event here, right? So in order to send the information that there is something here, we put a torch, and that information is received by eyes, and presence or absence of light would give you the information of presence or absence of the object, right? So these are the two very natural communication systems. But here, if you see, the carrier which you have used in order to send the information is light. Here, the carrier which you have used in order to transmit the information is acoustic wave, right? So the job of the transmitter is to identify the appropriate carrier. Transmitter identifies the appropriate carrier, and this carrier is used to carry the information. That is why it is called carrier, right? Carry the information. So how the transmitter decides the carrier? So from these two examples, you might have understood it, right? Because here you want to use ear of a person which can identify the acoustic vibrations, right? Air vibrations, and then convert it to the electrical pulses, right? Which B will use to extract the information. Similarly, here you are using B is using eyes, right? And I can identify the visible light portion or the optical portion or of the optical carrier. So you will use some optical carrier. So a few more advanced communication setup are, these are the basic communication setups, or I would say natural communication setups. The other advanced communication setups are when our base station is communicating with the mobile user, right? In 3G, 4G, we all use the mobile, right? Mobile phones. So, how this communication happens? Through radio frequency, right? Through RF waves. So the RF waves are used here. So, radio frequency is used for the communication here. Two computers also communicate with each other, right? Through wire. This is a wireless channel. So here the transmitter is base station, receiver is mobile station, and the channel is air, right? And the carrier which we are using is RF. And I told you that the carriers are decided by when you see that what type of receiver is that and what is your application. Mobile station can use the antenna in order to convert the RF waves to the electrical signal or the information, and the information here can be transmitted through antennas using the RF and by modulating the carrier or RF waves. Here, if two computers are communicating, the channel is wire, and when we can transmit our information to electrical pulses here, because electrical pulses travel through the wire very easily. So the carrier here is electrical pulses. So you might have understood till now that we choose carrier which carries the information by observing the type of receiver and also the type of channel which is used in order to transmit the information, right? Because here the channel is wire and we know that electrical pulses can very easily travel through wire. So we will just use electrical pulses. Here the base station and receiver are quite far and we want a wireless type of communication. And also the receiver is using antenna which can convert RF waves to the information or which can extract the information from the RF waves. And RF waves can travel far through the wireless channel. So here we will use RF waves in order to transmit our information. So these are the all the different type of communication systems, right? So do we have a very structured framework of a digital communication setup, or we have a block diagram which provides the different types of blocks which are used? So we have just seen this, right? This is transmitter, the channel, physical channel, and the receiver, right? What is there inside the transmitter, right? So we will be only focused on digital communication system or digital communication systems, meaning the information which we are transmitting is in the digital form, in the form of zeros and ones. And if it is not in the form of zeros and ones, we will first convert it to the zeros and ones. So if the source is analog, for example, picture, etc., or some wave, so we will just sample it and do the processing. We all know that, right? And we will have the digital form. So we will discuss the discuss two main aspects of the digital communication system. If we have a source, right, how should we convert the information content, or how efficiently we can convert, or we can represent the information, represent the information. So as I told you, the source can be either analog or discrete itself. If the source is analog, we can of course sample it, and we can have the discrete and we can have the discrete labels, right? Through sampling, and of course through quantization, we will not be having infinite number of samples. We will restrict our samples to be of finite size. So let the source carries three possible symbols or messages. Let the source S. You can think of this as I have a keyboard which has only three keys. So this key 1 corresponds to M1, key 2 corresponds to M2, key 3 corresponds to M3. Now I want this type of source to represent this, right? I want this to be represented in the form of zeros and ones, because it's digital communication system, right? So first we want our information to be represented in the digital form, right? Yeah, so this is discrete, not digital yet. So we have to encode these messages, right, in the form of we have to map each of these messages to sequence of bits, right? We can do this. We can maybe do this type of mapping, correct? So our first aim is to map our set M This is a scripted M which carries all the possible messages which this source can generate to the sequence of bits, right? And can be fixed for all the messages or it can vary. So this is called source encoder. So what is the job of the source encoder? To efficiently represent your source or efficiently represent the information in the digital form, right? Yes. Okay. So what type of mapping you must use here? Hmm. Okay. So this mapping firstly should satisfy the property that no two messages must have same type of mapping. Meaning the mapping performed for Mi should not be equal to Mj if Mi and Mj are not equal, right? Right? Why do we need this property to be satisfied by this mapping? Of course, because otherwise, when you map this type of symbols and again demap, if M1 and M2, for example, has same code, then when you decode it, you will not be able to make out whether it was M1 or M2, right? So it must satisfy this property. One more property which is important because here the source will generate these messages in a form of sequence. For example, as I told you, you can think of this M1, M2, M3 as the source which has only, I mean, as a keyboard which has only three keys. So one can generate M1, M1, one can press this key many times, M1, 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 then M2, then M3, and it can be any such sequences which the source can generate. So you should be able to, once you have this performed source encoding, any sequence which you generate here must be distinguishable when you decode it. Correct. So this source encoder must satisfy the property which is called uniquely decodability. Uniquely decodable code. The code must be uniquely decodable, right? So any sequence of bits or any sequence of messages must be identifiable at the receiver. So in order to make sure that the mapping which is performed is uniquely decodable, we restrain ourselves for the prefix-free codes. Prefix-free codes are the subset of uniquely decodable codes. So all prefix-free codes are uniquely decodable and they are easy to generate. For example, what is the why do we call it prefix free? Prefix free means no code word. So this is the message, and this we call code word. So if mi goes to SEMI. So this becomes code word, means the code word corresponding to M1 is 00 for this scheme or this mapping, SE1 for this SE2. If you perform this mapping, M1 goes to 00, M2 goes to 01, M3 goes to 10. So these are the code words and these are the messages. So no code word should be prefix of another code word. So there are tree-like structure which is used to generate prefix-free codes. So if we carry on with the previous example, we have three messages. So M1, M2, M3. If we put these messages here, what is the code assigned to it? 00. M1 will be assigned 00. M2 will be assigned 10, and M3 will be assigned 1. I think this is what we have used, 0, 1 and 10. Okay, so 0, 1 and 0. As you can see, no code word. So this is SEM1, or we just place M1, M2 here, and SEM1 becomes 00, SEM2 becomes 01, and SEM3 becomes 10. Right, so SE corresponding encoded symbol is this, encoded word is, or corresponding code word is this. In another example, we placed M1 here, right? So can we place M2 and M3 in the lower branches? The answer is no, because if we do that, M1, the code corresponding to M1 would become prefix of the others, right? So this is why it is called prefix free. So what will be the codes corresponding to this? M1 will be assigned 00, M2 will be assigned 10, M3 will be assigned 1. So these prefix free codes would be uniquely decodable as it lies inside these are the subset of uniquely decodable codes. But then the question arises, there are various SE exist, right? Or various encoder exist, which will map your source to the sequence of bits. So which one would you choose? This scheme or this scheme? Right? So in order to have a comparison, we should have some metric, right? So the metric which is used in order to identify the better scheme or better source encoder for this type of source, which we call discrete memoryless source. Discrete, of course, because it produces the symbols which are discrete, either M1, M2, M3. They are not continuous, right? Memoryless means the symbol or the message which comes out of this source at time t is independent what happened before time t. So it's memoryless. So in order to identify or compare two schemes, we define a quantity which is called average length of the encoder. Average length of the encoder. Average length means if you generate a very long random sequence of messages, then what would be its average length? So this source F generates, which is 3 keys or 3 messages, and we have given either this type of, these are two source encoders, first and second. So we need to find out what is the average length of each of these encoders. For that, we need to ask what is the probability of occurrence of these messages. Meaning that when you press these key buttons, do you press these key buttons uniformly? Meaning that out of, for example, 1,000 times, how many times you press M1, how many times you press M2, how many times you press M3? Do you press them with equal probability around this? If this is the case, that you press the buttons equally, right? You don't differentiate between these two. They are equiprobable. Then, so since there are three symbols, right? So what will be the probability of occurrence of? So we first ask what is the probability of occurrence of each symbol. So the answer is that they are equiprobable. So if the answer is equiprobable, means the occurrence probability of occurrence of message M1, probability of occurrence of MI we represent with PI. So since all the three symbols are equiprobable, so the probability is 1 by 3. So what would be the average length of the first encoder? What is the average length? This is called cardinality, this sign. Cardinality of a set M is the number of element in that set. Right. So for our set it is 3. And what is this L1, L2, L3? L1, L2, L3 is the number of bits of each code word. Right. So we want to know what is the average length. So probability of occurrence of M1 and the number of bits associated with it. A length of the code word. Li is the length of the code word I. So length of SEMI. So if you see for the first case, the length is 2 because all other code words have length 2. Therefore, the average length of this code word is 2 bits per symbol. 2 bits per message symbol. Correct? But what is the probability of the second? 1 by 3, 2 by 3 plus 2 by 3, which is 5 by 3. Bits per symbol, bits per message symbol, and therefore we conclude that average length, so number of bits on average required to represent your same source with source encoder 2 will be lesser as compared to the first. So of course you will choose second scheme, right? So as you know, the job of the source encoder was to efficiently represent your information or your message. You will of course go for the second scheme. Again, let's take the other scenario where all the messages were not equiprobable. Right here, in the last example, P1, P2, P3 was equiprobable, but now we make the assumption, it can be possible, right, that I press M2 more as compared to M1. Right, so I press M2 more, so probability of occurrence of M2, which we represent with P2, P sub 2, is more as compared to P1 and P3. If this is the scenario, so first you have to ask that what is the how these messages are distributed in probability, right? Or what is the occurrence of probability of occurrence of each message. Okay. So as we have already have two schemes with us, what is this scheme? It says M1, M2, M3 are the three messages. One scheme does this, another scheme does this, and the third scheme, the first scheme does this, right? 0, 1. As I told you that all of these are prefix free schemes. So we are now only discussing prefix free schemes, source encoding schemes. So M1, M2, M3. So 0, 0, 0, 1, 1, 0. For second scheme, it was like this. Because we have put M1 here, we cannot put anything below this. We put M2 and M3 here. Right? So third scheme will be one comes and he says, why not use 0 for M2? Means just swap M1 and M2. He says, I would create third scheme. I will put M2 here and I would just do this, right? I will swap M1 and M2 and I would ask what is the average length. So here the average length is 2. For this, average length will be, just calculate the average length. It will be 1 by 6 plus 2 by 3 into 2 plus 2 into 1 by 6. So it will be 11 by 6, right? Please check. By 6 bits per message symbol for this type of distribution, right? And if you go for it, you will see that L bar for this scheme is 2 into 2 by 3 plus 1 into 1 by 6 plus 2 into 1 by 6. 2 into 2 into 1 by 6. 1 is to 2 by 3. I beg your pardon, just. So L bar for this scheme is M1 is 1 by 6, 2 into 1 by 6. 1 is to 2 by 3 plus 2 is to 1 by 6. So you will see that it will be 8 by 6. So the average length of the third scheme is better as compared to first and second. So of course you will go for the third scheme. And what was the logic used for this? Since we have seen that M2, the probability of occurrence of M2 is more, so we should provide less number of bits to this. Because what is the meaning of average length? Average length means you need to find out what is the length of that encoding. If you do the encoding of your M1, M2, M3 and you generate a random sequence, what is the average number of bits required? Right? So for example, since we have seen that P2 or M2, the probability of occurrence of M2 is high, so of course you should provide less number of bits, because the phenomenon second or the message second is occurring more number of times, so we should represent it with fewer number of bits so that average length reduces. So what is the conclusion? That more frequent word, more frequent symbol or message must be mapped with fewer length code or code with less number of bits. So one would come to you and ask that what is the minimum value of average length? That one would say that okay, I have understood that. I would try to design my source encoder with minimum or less number of average length. But can you give me any threshold that this is the best case scenario? You cannot go below this. So that is the entropy of your source. So your L bars must be greater than equal to your entropy. Means the entropy, you cannot go below the entropy, and this is called source encoding theorem for any discrete memoryless source for lossless compression. Meaning that you don't want to lose the information, right? The aim of the source encoder is to just represent your information with fewer number of bits or the low average length, right? But if you try to reduce the mapping whose average length is less than entropy, then there will be losses. So what best you can do? You can go and you can try to reduce your average length, or you can try to design your source encoder with average length which is equal to the entropy of your source, right? So this is why we use entropy, and therefore efficiency of any source encoding scheme is defined by entropy of the source. So efficiency of any source encoding scheme is defined by the entropy of the source and the average length of that source encoder, right? So efficiency of any encoding scheme which we choose SE1, SE2, SE3 or eta of the efficiency of any coding source encoder is defined like this. Okay, you can calculate the efficiency of these three coding schemes. So what is the best you can have? 1, right? Or it will be less than 1, which is always less than equal to 1. And when your source encoder achieves the entropy, or you can represent your source with entropy, with source having average length equal to entropy, then your efficiency will be 1, otherwise it will be less than, right? Thank you.